The National Electrical Code does not provide a specific definition or method for calculating the hazardous current level from a capacitor discharge. The IEEE STD 463-1993 Recommended Practice for Grounding of Industrial and Commercial Power Systems provides guidance on estimating the hazardous current level from a capacitor discharge. According to IEEE STD 463-1993, the hazardous current level, I, for a capacitor discharge is given by I equals 3 multiplied by volts divided by R multiplied by T, where volts is the voltage across the capacitor in volts, R is the resistance in the discharge path in ohms, and T is the time constant of the discharge circuit in seconds. The time constant is the time it takes for the capacitor voltage to decay to 37% of its initial value. It is calculated as T equals R multiplied by C, where R is the resistance in the discharge path in ohms and C is the capacitance in farads. Let's look at an example. Suppose volts equals 298 volts, R equals 1150 ohms, and C equals 0.33 microfarads, which is 3.3 multiplied by 10 to the negative 6 farads. To calculate the time constant, we have T equals 1150 ohms multiplied by 3.3 multiplied by 10 to the negative 6 farads, which equals 3.815 milliseconds. To calculate the hazardous current, we have I equals 3 multiplied by 298 volts divided by 1150 ohms multiplied by 3.815 milliseconds, which equals 0.82 amps. According to IEEE STD 463-1993, a current level of 0.82 amps is considered a hazardous level for a discharge time of 3.815 milliseconds. Therefore, this condition is a legal hazard. The current flow from the capacitor discharge under the given conditions is considered a legal hazard because it exceeds the threshold set by IEEE STD 463-1993. Precautions should be taken to prevent accidental contact with the discharge path. It's important to note that the IEEE 463 standard provides guidance on estimating hazardous current levels, and actual safety practices may vary depending on the specific application and local regulations. Always consult with qualified personnel and relevant safety standards to ensure safe handling of capacitors and electrical equipment. The equation I equals 3 multiplied by volts divided by R multiplied by T is a simplified representation for estimating the hazardous current. The factor of 3 in the equation is derived from empirical data and represents a safety margin. The actual discharge current waveform may be more complex and influenced by various factors such as the type of capacitor, the characteristics of the discharge path, and the presence of any additional components in the circuit. Therefore, it's essential to consider the limitations of this equation and exercise caution when assessing the potential hazards associated with capacitor discharges. The time constant, T equals R multiplied by C, is a crucial parameter in determining the discharge behavior of a capacitor. A larger time constant indicates a slower discharge rate, while a smaller time constant indicates a faster discharge rate. The time constant affects the duration and magnitude of the discharge current, and therefore, it plays a significant role in assessing the potential hazards. The capacitance value, C, directly influences the amount of energy stored in the capacitor. A larger capacitance value means more energy is stored, which can result in a higher discharge current and a longer discharge duration. The voltage across the capacitor, volts, also affects the amount of energy stored. A higher voltage results in more stored energy and a potentially more hazardous discharge. The resistance in the discharge path, R, limits the flow of current during discharge. A higher resistance value reduces the discharge current and slows down the discharge rate. However, even with a high resistance value, a hazardous current level may still be reached if the voltage and capacitance are sufficiently high. When evaluating the potential hazards associated with capacitor discharges, it's crucial to consider the potential for secondary effects such as arc flash and thermal hazards. Arc flash can occur when the discharge current creates a conductive plasma, resulting in a sudden release of energy and intense heat. Thermal hazards can arise from the heating of components in the discharge path due to the high current flow. To mitigate the risks associated with capacitor discharges, several safety precautions should be implemented. Firstly, always de-energize the circuit and discharge the capacitor before working on it. Use a properly rated discharge resistor to safely dissipate the stored energy. Secondly, use appropriate personal protective equipment, including safety glasses, gloves, and insulated tools. Thirdly, implement lockout-tagout procedures to prevent accidental re-energization of the circuit. Fourthly, provide adequate insulation and isolation of capacitor terminals to prevent accidental contact. Fifthly, ensure proper grounding of equipment and enclosures to minimize the risk of electric shock. Sixthly, use shielded cables and connectors to reduce electromagnetic interference. Seventhly, implement surge protection devices to protect against transient overvoltages. Eighthly, provide clear warnings and labels to alert personnel to the potential hazards. Ninthly, train personnel on safe work practices and emergency procedures. Tenthly, regularly inspect and maintain equipment to ensure proper functioning. The IEEE 463 standard provides additional guidance on grounding and bonding practices for industrial and commercial power systems. Proper grounding and bonding can help to minimize the risk of electric shock and improve the overall safety of electrical systems. Grounding refers to the connection of conductive parts of equipment to the earth, providing a low impedance path for fault currents to flow back to the source. Bonding refers to the interconnection of conductive parts to create an electrically continuous path, reducing the potential for voltage differences and minimizing the risk of electric shock. The IEEE 1584 standard provides guidance on arc flash hazard calculations and mitigation techniques. Arc flash hazard analysis involves assessing the potential for arc flash events, determining the incident energy levels, and selecting appropriate personal protective equipment. Mitigation techniques include reducing the fault clearing time, increasing the working distance, and using arc-resistant equipment. The National Fire Protection Association (NFPA) 70E standard provides requirements for electrical safety in the workplace. NFPA 70E covers topics such as hazard assessment, personal protective equipment, safe work practices, and training. Compliance with NFPA 70E is essential for ensuring the safety of electrical workers. The Occupational Safety and Health Administration (OSHA) also has regulations related to electrical safety. OSHA regulations cover topics such as lockout-tagout, personal protective equipment, and training. Compliance with OSHA regulations is mandatory for employers to protect their employees from electrical hazards. Capacitor discharge hazards can occur in a variety of applications, including power supplies, motor drives, lighting systems, and electronic devices. In power supplies, capacitors are used to store energy and smooth out voltage fluctuations. In motor drives, capacitors are used to improve power factor and reduce harmonic distortion. In lighting systems, capacitors are used to provide a stable voltage for the lamps. In electronic devices, capacitors are used for filtering, decoupling, and timing circuits. When working with capacitors, it's important to be aware of the potential for both electric shock and arc flash hazards. Electric shock can occur if a person comes into contact with a charged capacitor. Arc flash can occur if a capacitor fails and creates a conductive plasma. To minimize the risks, always follow safe work practices and use appropriate personal protective equipment. The energy stored in a capacitor is proportional to the square of the voltage. This means that even a small increase in voltage can result in a significant increase in the amount of stored energy. Therefore, it's important to be extra cautious when working with high voltage capacitors. Capacitors can fail for a variety of reasons, including overvoltage, overcurrent, temperature extremes, and mechanical stress. When a capacitor fails, it can explode, release toxic chemicals, or create an arc flash hazard. Therefore, it's important to inspect capacitors regularly and replace them if they show any signs of damage or degradation. When disposing of capacitors, follow local regulations for hazardous waste disposal. Some capacitors contain hazardous materials such as polychlorinated biphenyls (PCBs), which can pose a threat to the environment and human health. Always handle capacitors with care and avoid puncturing or crushing them. In addition to the hazards associated with capacitor discharges, it's also important to be aware of the potential for electromagnetic interference, EMI. Capacitors can generate EMI due to the rapid changes in current that occur during charging and discharging. EMI can interfere with the operation of nearby electronic devices and cause malfunctions. To reduce EMI, use shielded cables and connectors, and implement proper grounding techniques. The selection of appropriate capacitors for a given application is crucial for ensuring reliable performance and safety. Factors to consider when selecting capacitors include voltage rating, capacitance value, temperature range, and ESR equivalent series resistance. The voltage rating of the capacitor should be greater than the maximum voltage that will be applied to it. The capacitance value should be chosen to meet the requirements of the circuit. The temperature range should be suitable for the operating environment. The ESR should be low enough to minimize losses and prevent overheating. When using capacitors in high-frequency circuits, it's important to consider the effects of parasitic inductance and capacitance. Parasitic inductance can cause ringing and overshoot, while parasitic capacitance can limit the bandwidth of the circuit. To minimize these effects, use capacitors with low parasitic inductance and capacitance, and optimize the layout of the circuit. Capacitors are essential components in many electronic circuits, but they can also pose significant hazards if not handled properly. By understanding the potential risks and implementing appropriate safety precautions, you can minimize the likelihood of accidents and ensure a safe working environment. Remember to consult with qualified personnel on relevant safety standards to ensure compliance with all applicable regulations and best practices. Proper training and education are essential for all personnel who work with capacitors. Training should cover topics such as capacitor construction, operation hazards, safety precautions, and emergency procedures. Personnel should also be trained on the proper use of personal protective equipment and the operation of safety devices. Regular refresher training should be provided to ensure that personnel maintain their knowledge and skills. In addition to formal training, it's also important to foster a culture of safety in the workplace. This includes encouraging personnel to report potential hazards, providing feedback on safety performance, and recognizing individuals who demonstrate a commitment to safety. By creating a safe and supportive work environment, you can empower personnel to take ownership of their safety and the safety of others. When investigating electrical accidents involving capacitors, it's important to gather all relevant information, including witness statements, equipment records, and environmental conditions. The investigation should focus on identifying the root causes of the accident and developing corrective actions to prevent similar incidents from occurring in the future. The investigation should be conducted by qualified personnel with expertise in electrical safety and accident investigation techniques. The results of the investigation should be documented and shared with all relevant stakeholders. In conclusion, capacitor safety is a critical aspect of electrical safety. By understanding the potential hazards, implementing appropriate safety precautions, and fostering a culture of safety in the workplace, you can minimize the risk of accidents and ensure the well-being of personnel. Remember to always consult with qualified personnel and relevant safety standards to ensure compliance with all applicable regulations and best practices.